In our previous video, we talked about how solar panels are made. In this video, we will talk about how these solar panels are manufactured on a large scale inside a solar plant. We'll take a look at all the processes involved in manufacturing solar panels, as well as the key equipment used in each process. If you enjoy this type of content, make sure to subscribe. Inside a solar panel manufacturing facility, there are two types of manufacturing lines: the mono line for monocrystalline silicon solar cells, and the poly line for polycrystalline silicon solar cells. The difference between these two types of solar cells is the raw material that they use, which ultimately determines their performance. In general, monocrystalline solar panels have higher efficiency than polycrystalline solar panels, but cost more to manufacture. For this reason, mono panels are mostly used in high-efficiency modules, while poly panels are used in standard modules. The first step in both lines is converting the silicon raw material into wafers. This process is called slicing. To do so, the silicon comes in the form of large cylindrical ingots, which are then cut into thin slices called wafers. These ingots are produced either by the Czochralski process or the Siemens process. In the case of monopanels, the Siemens process is used to produce ultra-high-quality monocrystalline silicon ingots with low defect density. The main difference between the two processes is that in the Siemens process, the silicon melt is not in a crucible, unlike in the Czochralski process, and the rotation of the crucible is what causes defects in the silicon crystal. So with this process, better quality ingots can be achieved. In the poly line, since the quality requirements are lower, the Czochralski process is used instead because it is cheaper. Both processes are explained in detail in another video. Once the ingots are produced, they go through a series of washing, drying, and cutting processes to become wafers. First, the surface of the ingot is trimmed with a wire saw to remove any damage from the surface. Then the ingot is put in an ultrasonic cutter machine, where high-frequency vibrations are used to cut the ingot into wafers. The vibrations help reduce heat buildup inside the ingot during the cutting process. Finally, the excess silicon on the sides of the wafers is removed and the edges are ground. This results in shiny, smooth-edged wafers ready to go into the next process. Wafers for mono and poly panels have different sizes and thicknesses. For instance, in the mono line, the size of the wafer is 211 mm by 211 mm with a thickness of around half a millimeter. In the poly line, the wafer size is 162 mm by 162 mm with a thickness of 1.8 mm. After the slicing process, the wafers move on to the diffusion furnace. Here the P-type mono wafers and the N-type poly wafers undergo an exchange process, where a phosphorus-based gas is used to dope the front side of the wafer, turning it into an N-type semiconductor. This process is called diffusion because the phosphorus atoms diffuse from the gas phase into the solid silicon wafer. After this, the wafers go through a series of washing and drying processes to remove any residues. At this point, the wafers are marked and screened to determine their final electrical orientation. To do so, a silver paste is screen printed on the back of the wafer. Then the wafer is heated and the silver paste fuses to the wafer. Next, an electrical test is performed on each wafer to measure its current and voltage. Wafer with low values are marked with an X and moved to a scrap container. Those with high values are moved to the next process. In the next process, the tested wafers are bused. This means that the wafers are electrically connected together to form one single unit. To do so, a metal bus bar is placed on top of the marked wafers. A conductive epoxy is applied on the bus bar and the wafers, then pressed together. This creates electrical connections between the individual wafers. At this stage, the bus bars are still separated and are attached to the pallets. The pallets with the bus bars are then placed into an oven where the epoxy is cured. After leaving the oven, the pallets are taken to a sawing machine, where the excess wafer is cut and removed with a wire saw. Then the bus bar is cut into individual solar cells using a diamond wire saw. The result is a solar cell with 5 individual sections interconnected and capable of producing direct current. Once the cells are cut, they are removed from the pallets and collected on trays for the next process. In the next process, the solar cells are washed and dried to remove any residues from the cutting process. After that, the cells go through a series of tests, including an electrical test, an L test, and a visual inspection to ensure that each cell meets the required standards. In the electrical test, the current and voltage of each cell are measured, and those with low values are scrapped. In the L test, an image is captured of the cell's light emission. With this, any internal defects inside the cell can be visualized, and any faulty cells are scrapped. Any cell that passes these two tests moves on to the next process, where any visible defects, such as cracks, scratches, spots, etc., are inspected. Those with defects are scrapped, while the rest move on to the next process. Here the cells are placed in an oven, where they go through a process called firing. During firing, the cells are heated to high temperatures. During this process, the aluminum frame of the cell reacts with the silicon wafer, releasing gases and leaving behind a thin layer of aluminum on the wafer. This layer is actually a highly doped P-type semiconductor, which makes the cell more efficient. After firing, the cells are immediately cooled down with cold air to avoid thermal shock. Then the cells are placed on a conveyor belt and pass through a washing and drying process to remove any residues from firing. Once clean and dry, the cells are ready to be assembled into modules. To assemble the solar module, several cells are connected together in series using a multi-bus bar interconnector. These interconnectors are made of aluminum and connect the cell's positive terminal to the negative terminal of the next cell, forming a path for the current to flow. The cells are electrically connected together in series to increase the output voltage of the module. The cells are arranged in a specific pattern depending on the number of cells per module. For example, for a 60-cell module, 3x2 arrangement is used. This means that 2 rows of 3 cells each are connected in series to form a module. Once the cells are connected, a front sheet of glass is placed on top of the cells. The cells are encapsulated in an EVA sheet on all 4 sides. The entire stack is then placed in an aluminum frame, which acts as a structural support and a heat sink. Finally, a back sheet is adhered to the frame. This encapsulating material keeps the cells protected from the environment and allows them to operate safely. After encapsulation, the modules are placed in an oven where they go through a lamination process. During this process, the EVA sheet is cured, bonding all the layers together. The temperature inside the oven is kept at around 120 degrees Celsius for 4 hours. After that, the modules are placed in an aging oven where they are kept at 85 degrees Celsius for 72 hours. After aging, the modules are cleaned and tested. Tests include an electrical test to measure the voltage and current, a load test, a thermal resistance test, a moisture test, an L test, and a visual inspection. After passing all the tests, the modules are ready to be shipped out. While this video was focused on the manufacturing process of mono and polycrystalline panels, there are other types of panels such as thin film panels. These types of panels use different materials and have a different manufacturing process. Overall, the manufacturing process of solar panels requires high precision and tight tolerances. The equipment and machinery used in each process must be regularly maintained and calibrated to ensure that the final product meets the required standards. Additionally, the entire process must be carried out in a safe and environmentally friendly manner. This involves adhering to strict safety protocols as well as minimizing waste and emissions. Despite the complexity and challenges involved in the manufacturing process, the end result is a clean and sustainable energy source that can be used to power homes, businesses, and even entire communities. As solar energy continues to grow in popularity, it is likely that more and more companies will invest in advanced manufacturing technologies to produce high-quality solar panels efficiently and sustainably.